welcome back. This is the ARM assembly course, and it's leading into us building a little mini ARM-like bytecode machine or virtual machine that we'll write in C++, and ultimately we're going to use that machine as our execution platform for our language in the compiler design course, and that's the reason I'm going down this path. I just decided that other tools like LLVM or even LibGit were just a bit too complex for working within the environment of a course, and I also thought it would be better to teach how the microprocessor really works by building our own little mini virtual machine. But to that end, we need to know a little bit, at least the concepts behind assembly language, and I don't expect this course to take you to a level of expertise at assembly. There's a lot of, it's actually, assembly language is surprisingly simple, but simple things can become complex very quickly. So there's, especially ARM assembly, the assembly instructions, there's not a lot of them. They're very simple and elegant and straightforward. But, of course, when you start building applications in assembly, it can get quite complex. Like so many things in this world, oftentimes the simpler something is, the more complex it can become as you build it up to those levels of complexity. So we're not going to go very deep into ARM assembly. This is really an overview and a look at it. We're going to write some code and show some basic concepts to get you to understand how registers work, how special system calls work, and how we manipulate numbers and values and memory addresses using assembly language. Then we're going to get into how we're going to construct from our compiler how we're going to construct executable code in assembly language in a simple byte machine. And we'll probably write a miniature assembler to test our byte machine with so that we can write some assembly code for that. But mainly we're going to work with it from our higher level language, actually putting the machine code, the byte code, into that machine. So to get started with this, if you want to be able to write the code I'm going to write, you're going to need to install some tools into Ubuntu. If you're using a different platform, you'll have to look these up. I've listed this all in the README file in the assembly course. GitHub repository that I've set up for this. This is open to the public. You can come here and you can read this. You can look at all the source code that I write in the course here. I will put a link to this in the description on the video, but it's github.com W Westlake ARM assembly course. It's pretty straightforward, simple URL. So I'm not going to go over this in detail or demonstrate it. It's simply a bunch of apt-get calls, or apt if you prefer, to install all this. What you'll be installing is cross compilers for ARM, and you'll be installing the cross compilers for the specific type of device that we're going to pretend we're working with here, which is these either the ARM Aqua Roadrunner boards or these Arietta Area and Fox G20 boards. Is what we're going to pretend we're working with. We're not going to get these boards and work with the actual boards. Eventually, what we'll do is work with a Raspberry Pi, which is also an ARM processor. But with the Pi, we'll be more interested, I think, in the functioning of the board rather than the assembly language level of stuff. So at some point in time, if people show interest, I might do some stuff with ARM boards at a lower level, or we do C code or assembly language talking directly to the board. So anyway, that's the GitHub page for this. And let me close this. This is where I wrote that all up. And so here's our project. Now, I'll talk a little bit about assembly language. Assembly language is basically a way of specifying very precisely what machine codes you want the computer to execute. Machine codes do a variety of things. They act upon registers and memory addresses. They perform mathematics, bit comparisons, bit shifting, and all this stuff. And they also jump the program or branch the program to new places to run in. And they keep track of conditions of things that have happened. And so I'll go over some of those details. I'll go over a little bit about the registers and the registers that are available and how we talk to those. So let's start by taking a look at a very, very simple program. And what's it going to be? Well, what do you always start with when you create a program? You start with Hello World, of course. And so I'm going to create a little folder here. I'm just going to call it Hello. And in here, I'm going to create a file called hello.s. And that's you can call it ASM if you want. I like shorter, abbreviated things. S is .s is a kind of a standard in the Unix world for assembly language, and ASM in the Windows world. But you can call it either. Unix doesn't care. The tools don't care what you call it. Just be sure that if you name it differently, you call the commands and stuff appropriately. So, an assembly language program is made up of sections, and there are some built-in kind of default, and we're working with GNU assembly for the ARM processor. So the syntax will be specific to GNU assembly. You'll see if you look around on the web at assembly language programs a number of different syntaxes. The differences are subtle. They're all pretty much readable as the same. The instructions are the same. It's the wrapping stuff that varies a little bit. So the sections are blocks or areas of memory that will be laid out by the assembler to hold different things, different kinds of things. So we can have data, and we can have what's called text, and text is program code. Okay, and there are other kinds of sections, but right now we're going to stick to those two. We're going to understand what a data section is and what a code section is. So let's start by creating a data section in our code. We're going to say .data, and that tells the assembler that we're beginning a data section. When we start a new section, that ends the current section that we're in. So when we start writing our code, we'll put a .text. That'll tell it we're starting the code section now, and that's all it's really for. So let's create a message label. The way you create a label in assembler is you put, and I wonder why this isn't showing. It's a .s file. I wonder why this isn't showing. Maybe do I not have GNU ARM assembly ARM support? I've got that installed. Azure C++ GNU. I don't know why it's not doing much in the way of syntax highlighting. You see, well, that's fine. I'm not going to worry about it. Maybe it'll catch up here. Once we've so the way you create a label for anything, this could be a label for a point in the code or a label in the data. Labels start with, and they mark a point of an address point. They label a point in the address. They're a name followed by a colon. And now we're going to use a special keyword, and it's .asciz. And we're going to just type, quote, hello. I'll do it the Kerningham and Ritchie way. And we'll go ahead and put a slant N at the end of that. So What's this saying? This is saying create myself an ASCII Z location, an ASCII 0 terminated bit of memory in the data section of code, and hard code into it. This hello world is hard coded like a constant into our program. Okay, it's going to be there. Now we got to do something a little tricky, and this is a bit of an odd looking syntax, but basically it is a way of saying that I want to do a little calculation and within the program. And this calculation isn't done during execution, it's done by the assembler. So I'm going to create a little variable here called len. This isn't a label. It's a variable within the program, and it's going to be dot minus message. And what this is going to do is let the assembler calculate the length of our hello world message by taking the current location, which is right after this, and subtracting this location from it, and that'll give the length of this. And if you put this right in immediately after it, you're okay, and we can tab that in. So it looks neat. Okay. So what do we need now? Well, we need some code, and we need to create a main function just like we would in C or C++. And so we're going to start our text section with a .text that just tells it, hey, we're going to start writing code, and then we're going to globally define our main symbol. And this just tells it main is a thing in the global namespace. And now we're going to create main, which is a label. Okay, ends with a colon. It marks a memory location, and this is the start of our program. Okay. And the very last thing I always do when I write C, and you've probably noticed this, or C++, is in my main function, I always create my return statement first to make sure that I exit the program correctly. So we're going to create that return statement here, and this is a thing in ARM. ARM has this ability to do software interrupts or system calls, and a software interrupt is their way of doing this system call. And there's a special register, so let's talk about registers now. The ARM processor has 15 registers. Several of those have special purposes and we can't use them, but most of them are wide open for our use, okay? And they're just numbered. They don't have any special names. They're R0, R1, R2, R3, up through R15. But like I said, we'll get into that a little bit. Some of the higher numbered ones are special purpose registers. One of them, however, is a special purpose register, but you can still use it for other stuff if you're not doing this. But that register is R7. And R7 is specifically used by a software interrupt to call a system command. And the system command that we want is system command number 1. So what this statement, oops, I typed move, it's MOV. What this says is move to register 7, the number 1. And that is a system call number, and system calls use register 7. We want to remember that. Register 7 is for system calls. It's not exclusively for that. If you're not doing a system call, you're more than welcome to use register 7 for other things as well. But if you want to make a system call, you have to use register 7. Okay, and then a system call is a software interrupt, number 0, and that will exit the program. That's what that system call does. And in fact, this won't print, but we're going to, it should anyway, build. So 1 second here, let me take a quick look at something so I don't get lost. All right. So I'm going to do this, I'm going to start by doing this manually. And actually, I'm going to pull up my Terminator console go maximize. Let's make it nice and big so you can see it. I know I sometimes forget to do that, and I know it can be very hard to read that little terminal inside of Visual Studio Code, and it won't let me expand the text in that terminal for some reason. So what we're going to do is type the following command: arm-linux, and now GNU EABI is fine. There's also an HF version of that, and the only real difference is for floating point and stuff. It's hardware versus software floating point math, but we're going to go ahead and use the hardware version of it since we're really running on a much more powerful processor. So this command, excuse me, this command is part of what you installed. ARM Linux GNU EBA IHF.AS is the assembler. Okay. And now what we're going to do, we don't actually have to type these flags, so I'm not going to bother. What we want to do is go -O. Well, you know what? I should have changed into the correct directory first when I opened this. Let's go into devel and is it ARM? Nope. It's assembly ls cd. I put it in projects. Yeah, ARM assembly. There we go. cd hello. Okay, so there's our hello.s that we created right here. This simple program. This won't print out hello world, by the way, but I'm going to show how it can be compiled. All right. So I'm going to go arm-linux GNU ABI, and that's fine, dash AS. We want to go we don't need to worry about that. Let me just double check so I don't type things wrong. So we're going to go -O hello.O, and it's going to be hello.s. And it created hello.O, and it compiled with no errors. So the next thing we're going to do is use the ordinary GCC, except it's not exactly the ordinary one. It's Linux GNU ABI.gcc, and we're going to use it as our loader. Yep, GCC. It's right here. And we're going to type in -O hello.O. And it compiled it. Now we've got right here this hello executable. I'll show that. So it's set as executable. It's colored green. However, if I type /hello and try to run it, we have a problem. LD linux.so.3. Ooh, that's interesting. Locate LD linux.so.3. Yeah, that's down in the ARM stuff. Yeah, it can't run it. It can't run it because it's not a x86 program. It's an ARM program for an ARM processor. If I was on a Raspberry Pi right now, that would actually execute right at the command line. Though I wouldn't have to use this fancy thing here. I could just use GCC because that would be on an ARM platform, and GCC on that platform is built for that platform. So I wouldn't have to cross-compile. I'm cross-compiling right now. So we can't run this. How are we going to execute it? Well, that's where we have this emulator that I put in here in the Very last of the installs is to put in QEMU user static. So what are we going to do with that? Well, what we're going to do is type in QEMU dash arm dash static minus L slant user slant arm slant user arm dash Linux GNU ABI dot slant hello. And it did nothing, but it did an error. It actually ran. So now that I've got those commands kind of on the command line, let's go back here and let's make this write our hello world program. So how are we going to do that? Well, there's several things that we have to do to accomplish that. And this is assembly language, so it's not simply a matter of calling print. However, there is a print available in the syscall. And that syscall is created by the assembler, but it's actually built into either our system, if we've got some sort of operating system, or QEMU in this case, which has the real basic stuff built into the platform that it's running on when it emulates the code. It's got these syscalls that you would find in a regular operating system, and one of those is the ability to print out to the terminal. Okay? And so we have to do some manipulation here. What we have to do is move to register 0 a #1. Now, that pound sign, that hashtag in front, is what tells the assembler that I'm placing an immediate value. I want to move this exact number into register 0, and it doesn't represent something else. It represents a numerical value. There are other symbols to reference memory and so forth, and we're going to use one of those right now. We're going to use an instruction called LDR, okay, which is load register. And we're going to load our register R1 with the address of message. So message is this symbol up here that's a label. It's an address of the beginning of this hello world string. And this LDR instruction says take the address of this and put it into R1. And then we're going to LDR R2 with equals len. So that's going to get len is a variable now, not an address. This is an address. This is a variable that contains the result of this computation, which is now the length of it. So it's going to take the value of len and put it into R2. And now we're going to do another syscall. So we're going to move to R7, a number 4. Now we could set up symbols, like we did here with len. We could set up symbols to represent these numbers so that they would have labels. But 4 is basically the print command. And we're going to call software interrupt 0. And then we're going to exit. Good. So let's go over here. And let's go back up to our compile command. There's our compile command. Bing. That quick. It compiled. It's a pretty small program. Now we've got to... oh. Nope, I did the wrong one. I wanted the AS first. That worked. Now I want the GCC. That worked. Now I want to execute it with QEMU arm static, and it says hello world. So what did we just do? Now hello world is slightly more interesting in assembly language than it is in C. It's a few more lines of code, and it exercises several key things. The ability to load a register, and I'll talk more about registers and what they do as we move along. To load registers with addresses and values from symbols, to call software interrupts. This is what you have to do. This is basically the equivalent of a print statement in C or C++, combined with this up here. It prints it out to the screen, as you saw. So we can... Now, that would be a real pain in the butt if I had to do that for every single file I created and make it into a .o and then combine those .os into an assembly. And so we're going to use a makefile to accomplish that. So real quick, I'm going to piece that makefile together and explain a little bit about how it works. So here at the top level directory, I'm going to create a new file here. I'm just going to call it makefile. And yeah, we're just doing this raw and simple. And I'm just going to copy paste this in to the makefile and explain it rather than typing it all out, because that's boring. Basically we have now I changed the name here. I called it source. I want my output directory bin to be bin. These are just names I made up, by the way. In this case, my source is going to be in folder hello. Our C compiler I've set up in here in case we want to, crunch some C, C++, is going to be G++, but for the ARM. This is our assembler, and this is our loader. We're using GCC as our linker loader. That links the programs together. And then we've got some C flags here because it's going to set the CPU to a Cortex A72. I'll talk about that a little bit. These are different kinds of ARM devices. I didn't use them below, but we weren't doing anything that a basic ARM couldn't do anyway. And then I've set the float to ABI hard, which means it's in hardware mode. And that's what I'm using up here now is the hardware versions. I think I used the ABI version before. And now we've got hello world, but actually we just have hello is our file. Now these commands, they just rip through all the CPP or .s or .asm files and compile them into appropriately into O files. And this final command here creates an output file that's going to be called boot, probably. I think that's what I named it. And then link it all together, and we'll just have a single one called boot. So now that we have that makefile in place, if we go make, I think this will work. Minus O bin hello, yeah, that worked. Fatal error, can't create file. Bin hello, no such file or directory. Make dir bin. This doesn't make these automatically, by the way. There it is, now compiled. And now we've got this file right here called boot. If we look in ls hello, we've got that hello down there. I'm going to remove that. ls hello. Yeah, we don't need that anymore. Now we've got this boot here, which cannot open shared object file, so forth. Yeah, it's can't run on that platform. And now I've got one other neat little script I wrote here that'll make life a little bit easier for us, and it's just called run sh. So we're going to go over here and just create that. We'll call it, actually I called it run arm.sh. And I'll copy paste this in as well and then explain it. So it's a very simple bash script that saves me from having to type out all that QEMU stuff. So basically, it checks to see if $1, which is the parameter, has something, because you need to specify a file name, and it prints out the usage and exits, or it goes ahead and runs that same command arm static, and this can be used to print out the error, the result of that run if you want. So in case it errored. So now we can go oh yeah, we have to make that executable. Chmod u plus x run asm.sh, and now run.asm.sh. We get the usage /boot and boot error while loading shared libraries. Live cannot open shared object. Interesting. Why? That's interesting. Oh, ABI. It's got to be ABI HF, I think. There it is. It worked. Okay. Yeah, I had changed this to just the ABI because I was doing something else, and where I took this from here, I'll have to be sure I fix that in that other repository, because we're using the hardware version, not the just regular EABI one. So that's it, I think, for this video. We did quite a lot. Let me see how much time we're into it here. Yeah, we're 32 minutes. So we kind of went over a little bit about the basics of assembly. We'll do a little bit more in assembly, just to learn a little bit about branching and some calculations and comparisons and stuff. And we'll do that by making some decisions about what goes on in here. And then that'll probably be it for the assembly part of this. Maybe one more video. And then we're going to start getting into how could we build a machine in software to do this, to pretend to be another computer and run these kinds of levels of code that we can store as a machine code file and load it into it and have it run. So very similar to QEMU, although QEMU that we've installed here is a very, very powerful virtual machine. It can do a lot. You can run operating systems in it and stuff. Ours won't be that powerful. So anyway, thanks for watching. I hope you enjoyed the video. If you liked it, hit that like button. If you really liked it, hit that subscribe button. And I will see you in the next video. Thanks for watching.